That's okay. I just want to know where to press it now.
I should stay in a fixed position. Yeah, it's fine. I'm standing. I will be standing. Mm-hmm. Okay.
I think we can start with the afternoon session of our school. We are very happy to have here Professor Renate Loll from the Radboud University in Nijmegen, the Netherlands. She's a renowned expert in many issues related to quantum gravity, so we're very happy to hear her introduction on the topic. That will be 2 hours today and 2 hours tomorrow, I think, no?
Wednesday.
Wednesday, sorry. Okay, thank you.
Okay, I feel a bit naked, not maskless, but I think it will help to understand what I'm saying. So I'm also happy to be here in front of real people. It's a little bit unusual, but I'll do my best. So I was thinking about what precisely, to tell you. It's a very mixed crowd, which is kind of, anyway, unknown to me. That's what I'm guessing from the program. So I need to be basic, but on the other hand, I want to cover some ground. Yeah. So I've chosen for compromise and I've organized it around questions that. Good questions, well motivated, at least in my mind, around which I'm structuring, giving you some information about quantum gravity, the fields, the origins, the techniques, etc. So I hope it'll work. Today I'll try and cover 15 questions. How many there'll be on Wednesday, that remains to be seen. Yeah, if you have urgent questions in between, in addition to my questions or follow-up questions, just raise your hand and tell me. Okay, so what would be more appropriate than in these times? To start with some health warnings. So number one, quantum gravity is of course not a textbook theory in the sense that it's still a theory in progress and we haven't understood fully what it is, what type of theory. It does also require a lot of background knowledge to really work with it. I can just start with the obvious is classical GR, general relativity, but many more things. Obviously, quantum theory, quantum field theory, whatever, functional analysis, statistical physics, depending on which way you want to go in quantum gravity. So as I said, I will try to cover a range of issues, but I cannot be possibly comprehensive. Yeah, and there won't be time to derive any results. And if you are allergic to lecturers who don't derive results, well, then these lectures will not be for you. Yeah, of course, there is lots of literature and still on everything I'm saying. If anyone has specific questions about the literature, please come to me afterwards or ask me tomorrow during the problem session. Well, I myself have been doing quantum gravity from a variety of points of view for a very long time, decades, and inevitably and fortunately, of course, this has shaped my view on the subject, also, on its future promise, prospect, and also some of the problems. And of course, to that extent, and to the extent that the theory is not a settled theory, not everyone will agree with some of the views I will express. I will, again, generally give you health warnings, but I'm not going to say very outrageous things. So there's no general consensus on which approach to take, which road to take. However, I should say there appears to be some progress in the sense that people are somewhat less arguing than they used to about what is the correct approach, because blah, 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 then come a long list of one-liners why approach X clearly must be wrong and Y clearly also must be wrong, but your own approach Z clearly has a great chance of succeeding. So one is moving to somewhat more fruitful things about, what actually other predictions we can derive, maybe not yet in the sense of full, phenomenological predictions that we can go out and measure in astrophysics, but kind of things, kind of observables is the key word. We can try and compute within our different theories and then compare. And that already may give us some information of what's going on. And so that's a very healthy direction the field is taking. Okay, so I'll guide you through the jungle, and we start, of course, with the key question. What on earth is quantum gravity, Q1? Okay, so it is the fundamental quantum theory underlying Einstein's theory of general relativity. So we are really arguing in analogy with everything we know about the other fundamental interaction. So what we want to do is to understand and also describe in a quantitative way the structure and the dynamics of space-time, which is the same thing as saying the gravitational interaction. And a fundamental theory should be able to do this on all scales, and very importantly, the very smallest, so the so-called Planck scale. And I like to start my talks with this nice logarithmic scale, the kind of things we theoretical physicists are interested in, stretch over a vast range of scales. You see of almost 60 orders of magnitude. Here's the visible universe, 10 to the 24. Solar system, that's us, 10 to the 0. Atomic physics, nanoscale, 10 to the minus 19 meters are the distances we can resolve with our current best particle accelerators. Cosmic rays, have energies that go further than that. Kind of, so the universe is still a better accelerator than the LHC. And here at 10 to the minus 35 meters is the Planck scale. So the infamous habitat, as one says, of quantum gravity. Now, what is the role of gravity throughout these scales? Well, gravity is weak. However, when you go to the largest scales, all the rest has died away, and it dominates kind of the large scale dynamics of our own universe. So that's what we're familiar with from cosmology. Now, all the way down to centimeters, millimeter scale, gravity works just fine. Even kind of Newtonian type gravity works just fine. Then, because gravity is so weak, once we enter atomic and nuclear physics, it doesn't seem to play any role at all. In part because it's so much weaker on short distances compared to the other forces, the nuclear and of course also the electromagnetic force, until, well, we reach then these magic 10 to the minus 35, where no one can as yet go. And perhaps it dominates also scales, something I'll hope to say something about later. Now, what this doesn't necessarily imply, and we do not hope it implies, is that necessarily all quantum gravity effects are confined to a tiny, essentially inaccessible region, which you of course cannot probe directly and presumably never will be able to. So what one hopes for is phenomenological predictions of quantum gravity that one is able to tie to more macroscopic physics, in the sense of making predictions of, hopefully extrapolating something an effect that might be seen in the next generation of gravitational wave observatories. Yeah, I'm saying this is optimistic, but this prospect alone has given also the field of quantum gravity really new energy, yeah, new momentum, and people trying to think creatively, where one could go. And again, that's very good for the field, that people try and think again in tangible terms about quantum gravity. So we are hoping for macroscopic signatures. So why are we interested in quantum gravity? Well, general relativity doesn't seem to be quite good enough in terms of questions we can ask about space-time. So there is this adage, it says it predicts its own demise, that refers to kind of the famous singularity theorems of the classical theory, for which Penrose, it's almost the stuff that Penrose got the Nobel Prize for recently. But so general relativity predicts these very general singularities, and there the theory doesn't seem to make sense anymore. So one then asks, okay, at the very shortest distances, perhaps at very large energies, kind of translating this to physical situation, maybe another theory should be taking over that's more fundamental, and that should be a quantum theory. And that is then quantum gravity. And hopefully it will enable us to answer questions about, tracing the history of our own universe, just this little bit further back in time, yeah, to higher energies, and hopefully say something about the origins of our universe, more than we can say currently, where gravity is kind of treated classically. Of course, you can also ask, just don't go to the beginning of our universe, but if I examine just a piece of empty space-time on shorter and shorter and shorter scales, eventually, what would I see kind of in terms of a non-trivial microstructure? Again, using ideas somewhat heuristically we are familiar with from other quantum field theories. Yeah, think of the QCD vacuum. Is there an analog for gravity? So is there a structure where space-time itself then becomes very quantum fluctuating, and then perhaps doesn't look any more like a classical space-time at all? So let's forget about G mu nu, perhaps, and let's dream about some quantum space-time form full of wormholes and fanciful structures. Now, the question is, of course, from the point of view of physics, is this something I can describe quantitatively? Can I build models? Can I build up a theory that has such properties? And what are they? Can we check these heuristic ideas? Now, very fundamental questions have to do with the fact that gravity is a theory of space-time. So we could also imagine that properties of classical space-time we are taking for granted as part of general relativity become, number one, dynamical, and maybe disappear altogether when we go to very short scales. So that would then say, okay, can it be that I have some microscopic degrees of freedom which I maybe don't even recognize as having anything to do with gravity? Could it be that from such structures emerges in some magic way time, causality, what have you? Is structure we see in our own universe, could the structure be purely gravitational? I mean, that would be very exciting, but very interesting. Yeah, some kind of structures within very early space-time itself, and maybe giving rise to inhomogeneities. Now, and lastly, really, can we come up with observable quantum gravity effects, as I've already mentioned, and that might conceivably be visible in the near future? Okay. Question number 3. Why do we not have a quantum gravity theory yet? And well, of course, I could speak all afternoon about it, but let me make a sub-selection of kind of stating some of the more obvious points. So structurally, really gravity as a field theory, quantum field theory is really very different, because all of a sudden space-time becomes dynamical. Whereas in the other fundamental interactions, we're just working with space-time as an inert a background. And kind of standard quantizations we are applying, real textbook stuff, right, quantum field theory, are really tied to having a flat background where you can set up the whole paraphernalia of relativistic quantum field theory, which uses in an essential way the fact that there is global Lorentz and Poincaré invariance. Yeah? So it is really not made to talk about dynamical spacetime, and neither have people felt for a long time that it was particularly relevant. So if we, do scattering experiments at the LHC, who cares about gravity, as I already mentioned earlier? So you may want to compute some, quantum gravity corrections to your scattering amplitude, but they are so small they're completely irrelevant, just because gravity is so weak. So of course one could take the point of view, well, what do I care about quantum gravity? Anyway, it happens at a scale that is kind of ridiculously small. And well, let's just examine for a second where this smallness comes from. Well, it comes from the weakness of gravity. So I've said that a few times. So just take Newton's law of the gravitational attraction between two masses, classical masses M1 and M2, right? Then we have this fourth law, force proportional to 1 over r squared, where Newton's, the gravitational coupling constant, appears. So this is a dimensional coupling constant, but you see it's small, kind of in everyday units, 10 to the minus 11 here. And this is one of the constants you stick into deriving this Planck scale, which is the unique scale of the dimension of a length you can construct from G Newton, h bar, and the speed of light c. And so here's the formula, and it comes out, as I said, just ridiculously small, namely that this is a 10 to the minus 35 meters we saw earlier on my logarithmic scale. So in practical terms, we have no experiments really to guide our search, which we know has been extremely important in the development of our theories. Yeah? There is no phenomenology out there that is crying for a quantum gravitational explanation. So another reason for maybe not bothering about quantum gravity, a strong technical reason relating to what I started talking before, is that the standard perturbative quantization doesn't work. So if I implement it, just make a weak field split of the metric G mu nu, we'll talk more about this later, I don't find a consistent fundamental theory because of this famous non-renormalizability result. And then the question is, well, where do we go beyond that? I mean, there's not a standard route that everyone would agree upon. And of course, given all these extreme scales that are involved in quantum gravity, one might really ask, well, is this still within the realm of theoretical physics? I mean, with current technology, mathematics, can we really say anything meaningful about physics at the Planck scale? And of course, what's used more kind of in the popular literature, could there be some fundamental incompatibility between gravity and quantum theory? That's not exactly a good way of phrasing things, but that's how people often talk about it. Yeah, they're thinking of things like, okay, when space-time is dynamical, time is dynamical, whereas when I do quantum mechanics, there's always that one time, or even when I do quantum field theory, there is just a class of times. Now, what happens with that in gravity? So are there fundamental incompatibilities between the fundamental principles these theories build upon? Okay. let's move on. Now, are there specific properties of the classical field theory of general relativity that foreshadow kind of that we might find problems in quantizing, in inverted commas, the theory? So where I say quantizing in inverted commas, because we don't have a kind of crank, we don't have a machine where you stick in a classical theory and out comes a unique quantum theory. So such things don't exist. But nevertheless, it's a meaningful question. And I would say the answer is yes. So gravity is in essential ways different from the other fundamental forces. So let us zoom in on something I haven't yet mentioned, which is the so-called universality of gravity. What does that mean? Well, gravity, well, everything, all forms of matter and energy interact gravitationally. Yeah? This is to be contrasted with something like, electromagnetism. You need, let's talk about electrostatics. You need a charge in order to feel the force. If the charge is positive, or if two charges are positive or both are negative, then you get a repulsive force. If they are opposite, you get an attractive force. If they're neutral, there's no force. So when we translate this kind of to gravitational context, it would say, well, everything has is charged just by virtue of having mass and energy. And gravity is always attractive, kind of relentlessly attractive. Whatever you do, put things in a room, switch off everything but gravity, they will tend to lump together, unless there are other forces at work. Now, the universality of gravity, the fact that it universally kind of affects everything, enables us to reinterpret it as a local structure of space-time. And that's exactly what general relativity does. It interprets these gravitational properties as curved space-time. Yeah? So that's, of course, really why we are talking about space-time being dynamical. Yeah? And the structure of that space-time being described usually by a metric, a Lorentzian metric, right? This is, of course, captures kind of classically the complete information there is. So everything we want to know about gravity, gravitational forces can be captured in these geometric terms. So it's a theory of space-time, not on space-time. And here also the famous adage, the stage becomes the actor, right? So what used to be just a kind of a flat background, that's how we always thought about space-time just being there, in the Newtonian picture, but also later in a special relativistic picture, is just Minkowski space just being there, becomes a dynamical entity. And yeah, so space-time can bend, curve, and oscillate. And of course, a very famous prediction, which is of course not there in Newtonian gravity, are gravitational waves, about which we've heard a lot in recent times. I've already said, also the standard machinery of relativistic quantum field theory works for flat Minkowski space, but is not immediately applicable in a more general context. So one has to think about what to do there. And outside, so as I said, one never really considers anything but flat Minkowski space as a background for the other fundamental forces outside of cosmology, because in cosmology, we want to say, okay, we're studying quantum fields on an expanding universe, some kind of de Sitter type. So there one has to go a little bit further, but nevertheless, gravity is not usually treated as dynamical there either. So that's the next step. Oops, it looks as if I was on a scale. Okay, have I been here? Did I go back by mistake? I don't know what happened, but here's the next question. So all these specific properties of classical gravity, there was a slide missing. And what I was saying on the slide is that gravity, just taken as a classical field theory, is a very complicated theory. Yeah. Take a scalar field means, a field where I specify one number at a point. Now here, I now go to a scenario where Lorentzian space-time metric. So that's a two-tensor, a symmetric two-tensor that is not allowed to become a degenerate. It's symmetric, and by taking two derivatives, I arrive at the Riemann tensor. Yeah, the Riemann tensor is a horrible four tensor, an object with four indices, which in 4 dimensions has 256 components, which capture all the ways, space-time just locally can be curved, which we probe by doing parallel transport in all planes with all kind of orientations. Yeah. It's not that the 256 were all independent components, but still a good number of them are. So that just shows you the complexity of this as a classical field theory. Then we write down the Einstein equations. There are a very complicated, highly nonlinear set of partial differential equations, of which we do not know the general solution. Yeah, the solutions we know are very symmetric, typically. So our expectations should also be somewhat framed by our knowledge of these properties of the classical theory. Yeah, and just think of, nowadays, right, people talking about binaries. Binaries, that are sources of gravitational waves, generate in their vicinity extremely strong gravitational fields that we are unable to describe analytically. Yeah? So we have to invoke numerical methods to understand, right, really the process, to get a quantitative understanding. So, and this is just the classical theory. Okay. Now, so am I not just talking about technical issues, technical problems? In a way, yes. So when I said, look, standard relativistic quantum fields very essentially need Poincare invariance, but one can think of generalizations. And one can do this in various ways. One can put in a background, but then show in the second step that the setting up doesn't depend on the choice of the background. Yeah? Something like that I would call implicitly background dependent. One can try and work with other variables, other setups, where one can talk about the space of all geometry in a natural way without putting in explicitly any background. So there are ways and means people have explored for quite a number of years or even decades, where geometry is dynamical. There are also statistical systems that people are studying where also geometry is dynamical. Now, I want, however, to highlight a specific source of problems. Why I highlight it? Because it's not usually seen as even an issue classically, but it becomes a quite profound difficulty quantum mechanically. And that is, if you like, the symmetry structure of general relativity. So, of course, we have this very powerful classical model of how we describe gravity classically, the structure of space-time. We use the framework of differentiable manifolds. Yeah? So what's the essence of a differentiable manifold? Well, kind of it's a smooth differentiable manifold, smooth, and it has a property that locally I can describe it by putting just a set of coordinates, kind of choosing coordinate patch, and I can really do all my computations, although this might be a curved space, I can do them in such charts. Yeah? And why is that nice? Well, then I can write down my differential equations, I can try and solve them. Yeah? So, but it's not just, but of course the curvature plays a role because I still have a non-trivial metric floating around. But what is also the case is that it's just my choice how I parameterize locally in terms of coordinates my curved manifold or just the neighborhood of a point of that manifold. And classically, so I have the metric. Here is now the Riemann curvature tensor in its full glory. We can choose any coordinates, and it will not affect the physics of gravity. So the gauge transformation, if you like, it's like misnomer because it's not a gauge transformation in the sense of local gauge transformation like in QED or QCD, but nevertheless, an infinite dimensional symmetry group is that of the so-called diffeomorphisms that you can think of when you go to local patches as kind of coordinate transformations. Now, what does it mean? It means, so G mu nu itself, since it entries transform non-trivially, is not just, well, it's not observable in a way, but it's not physical. So of course there is physical content in it, but there's also kind of redundant kind of gauge content in it. And even classically, people have often been fooled interpreting kind of G mu nu, staring at G mu nu, and claiming or a curved space has certain properties, whereas there were just kind of coordinate effects that kind of go away. And the famous example I'm naming two here from the history of GR. So there was a long-standing confusion about the status of the event horizon, right? What happens there? You could say that continues kind of in some context even to today. But even the question whether gravitational waves are a real physical phenomenon confused even Einstein. Yeah? So there are false claims written in this famous paper with Rosen. So there are pitfalls even classically distinguishing between what is kind of just a coordinate effect and what is the true physics. So how do we understand, what the true degrees of freedom of general relativity are? So sometimes it's even important in understanding kind of classical curved geometry, but it becomes even more important quantum mechanically, and I'll tell you in a second why. So here we have, here we have the gauge group, the so-called gauge group of diffeomorphisms. I call it diff M. And here I'm reminding you what happens if I change local coordinate patch from coordinates x to y. Yeah, I have here the invariant line element that really measures invariant distance. Yeah, but I write this as this contraction here with the G mu nu and the coordinate differentials under this coordinate transformation assumed to be 1-to-1 and usually smooth. Usually one works in the smooth category. You see, it leads then in new coordinates y to just a different functional form as a function of these new coordinates. So if you look at this and you look at that, just staring at things, you don't really understand that they're one and the same geometry. Now, classically, we often think of this property as a nice property. We call it the freedom to choose coordinates. So the freedom to choose coordinates, for example, to make the equations you're trying to solve, typically Einstein equations, look maximally simple. So if you have a system that has a certain symmetry, you will choose adapted coordinates that make your equation look simple. Yeah, make them ODEs instead of PDEs, for example. Yeah? So it's nice. It's something we are happy about to be able to do in the classical theory. However, when it comes to the quantum theory, these extra degrees of freedom are nothing but a pain in the neck. Yeah. So to give you an example, in the path integral, we're doing functional integral over all configurations. Now, if I do that just over G mu nu, of course, there are directions which are gauge directions in which nothing happens, but they all contribute infinities to my path integral. So I need to gauge fix. And then I have to be careful. I do this in a way that the gauge is a good gauge, so it's unique and attainable. And I have to still be careful that I don't claim I have results which in the end just turn out to be gauge dependent. So there's a host of difficulties, and I would say, you could say even more elementary is the question, if I have now, a quantum theory of gravity, how do I represent this symmetry? A global symmetry, I would typically say, okay, it will be unitarily represented on my quantum fields. But unitary irreducible representations of the diffeomorphism, well, that's already it's not an easy object even to start thinking about. So what do I do with this symmetry? Yeah.
Somehow it resembles the problem which happens in gauge theory. In theory, you also have you need to fix the gauge. So
yes.
It's more complicated, but it is not unusual.
No, it's not unusual. But I've been saying, I kept saying, the fields are not a gauge symmetry, and that leads now to a slightly different notion of what you mean by an observable. Yeah. So I'll come to this. So observables are, of course, invariants under the symmetry. So of course, in QCD, or I can find local scalars by just tensing together fields appropriately, or I look at Wilson loops and such things. Now, what are observables in gravity? They're ever so slightly different, which makes life more difficult for us. Okay, so there is a way, a way of thinking of that slightly abstractly in mathematical terms that says, well, look, the true dynamics of general relativity doesn't take space really a place on the space of all metrics, Lorentzian metrics, which are called kind of law M. So M is my four-dimensional differential manifold, but really a physical configuration is an equivalent class of metrics, where when two metrics are related by diffeomorphism, I regard them as one and the same physical configuration. So that's expressed by using these square brackets. So the space of these equivalence classes is kind of the real physical space. Yeah, this is, of course, the space of geometries. So that's quite a usual kind of way of writing this. And geometrically speaking, of course, we're talking a lot about finite dimensional configuration spaces. These are fields, they're infinite dimensional configuration spaces. Yeah. So this is a kind of a sketch of what the Lorentzian space of metrics looks like. Now here are kind of the orbits under the action of my invariance group, namely the diffeomorphism. So G mu nu's that lie along the same orbit are physically equivalent. So, and that again, the square notation. Now, the space of geometries is not really a nice or a linear space, a vector space. So adding two objects doesn't necessarily land you in the space. I think that's again not too different from what happens in true, say, non-abelian gauge theories. If you want to think about it in this way, we also don't really have nice coordinates on the quotient. I mean, the two things are related somewhat. And if you're now asking for classical observables, well, you can say, well, they're all functions on G of M, or equivalently, they're just functions of my classical field configurations that are invariant under the action of the diffeomorphism group. Now, the notion of diffeomorphism that's really relevant also in the quantum theory is that of active diffeomorphisms. So you're really thinking of, I have my manifold M, the diffeomorphism maps in a one-to-one manner each point onto another point and in a smooth way. So this notion of a diffeomorphism is not local. So here it's really where the difference with Young-Mills comes into play. Yeah. So it moves points in addition to generating kind of a frame rotation. As a result, so if you are really working, say, in pure gravity, so you don't have any external reference frames, you don't have, boundary conditions that are defined by something sitting there. Yeah. Observables that are invariant under diffeomorphisms are very non-local objects. Why? Well, the point X is not a physical notion with respect to diffeomorphism. So the point gets moved. So even if I say, let me think of the Ricci scalar at the point x, that x and that x gets moved, that is also not an invariant concept. What is an invariant is the integral over all of space-time of the scalar. That's a bona fide invariant, but it has the very unpleasant feature of just being very non-local. I mean, it's a full space-time integral. Yeah? So that's really, a key difference with Yang-Mills theory, and it really leads also to issues in the quantum theory, because the same argument will apply there. So quantum observables will also be very non-local objects, and that's not a situation we're usually faced with in other common field theories. Yeah, question.
So this is a question, because it's non-local, we can't define like an algebra for the space-time.
I cannot define a what?
You cannot define like an algebra for the
An algebra of what? Of observables?
like if you consider the group space-time as like an analogy to these groups, you cannot define something like the algebra.
You mean now the configurations? I'm not quite sure what the question is. So I have my physical configuration space, right, which is this space of classically the space of equivalence classes. Observables are just functions on that space. And now your question is.
So if I understand correctly, you can take the function of that space
Mm-hmm.
as like a group of diffeomorphisms, and can you define an algebra of this group?
I'm not sure whether you are, well, the space of all observables is, well, it's just a function space, so can give it. Maybe, yeah, maybe you come to me afterwards and explain why. I'm not fully understanding, I think, the question. Okay. 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 Other questions about this point? Okay. Now, let's move on to question number 7. A small jump. So, I've talked about there is a standard way of quantizing, and that standard way is really the textbook quantum field theory way of quantizing. And one might ask, and when I think when I teach quantum gravity at my own university, I'm conflicted because I tell my students a lot about stuff about the perturbative quantum field theory. And well, they don't tell me, but I have the idea they probably think, why should I learn this stuff? Because it's, everyone knows that this is completely irrelevant because it doesn't lead to a full theory of quantum gravity. Yeah, on the one hand, this is correct. However, there are a number of good reasons why you want to look at it anyway. Of course, if you want to improve on something, it's maybe good to understand how people have thought about quantum gravity really for the last, since the 1930s. So, number one, this perturbative framework still, presumably, is good and valid in kind of the modern way of thinking about quantum field theories, where everything comes with, not an expiration date, but with a energy interval where it's valid. Huh? Okay, so in that sense, you can say, well, if depending on what process I'm considering, if I just stay far enough away from the Planck scale, it still seems like a good, and I just truncate my perturbation series, it's maybe still a good prescription. So, and in that sense, it's still studied and used a lot. Well, I would say it does not necessarily mean that the computations you can do in this framework are necessarily useful or well motivated, or testable. Why is that? Well, it's still one of the problems is, of course, still the weakness of gravity, and then therefore the weakness of any quantum gravitational effects. Yeah? So many people, for example, have studied quantum corrections to Newton's law. Yeah? And one has now agreed, I think, more or less on the coefficients are in the relevant terms. Yeah? But still, number one, the effect is so tiny that there is not really any way of verifying it. Yeah? It raises further questions. Is it really meaningful? Are the concepts, if maybe there's in principle some issue with us using these concepts, but not deriving at any testable consequences? So, yeah, well, it's not so clear that it's useful, at least. You know, truth is a whole different matter, but usefulness is a good criterion in quantum gravity. Okay, if nothing else, studying this perturbative quantum gravity will give you a good idea of what I've emphasized is true for the classical theory, is true also for the quantum theory, even just in the linearized case. So, perturbatively, of course, you set it up, right, with the kind of Feynman rules, but where then, of course, you have to gauge fix, etc. Yeah. Number one, you will learn about the classical starting point, which is really linearized gravity that describes gravitational waves. So that's a good benefit. On this, you then build basically an action principle. Yeah, that is based on the so-called Fitz-Pauli Lagrangian action, and that goes back to the 1940s where people have studied it. So everything is linearized. So everything works with the linearized fields. You use linearized diffeomorphisms. Then you have to gauge fix. Yeah, you have to get rid of redundancy. You have to be really careful that you gauge fix in the right way. And then it turns out, well, you have to really compute and use Faddeev-Popov determinants, which are basically, you know, the Jacobians of the transformation that gets you from the original linearized field variables to kind of a split into, yeah. For putting in a mass, well, then it's not gravity. There, of course, I mean, if you're referring, people, of course, play around with lots of variations on general relativity, right? Where various properties are relaxed, and you can try and give gravitons a mass and see, yeah, where that leads you. I will not touch on this, right? So that's more, you know, it's the whole, you know, story of alternatives of gravity. So what I'm working on is really, number one, the statement, I mean, really classical GR is the correct theory of gravity. And then how do we quantize it? But there is, of course, a whole universe is kind of tangential to the story. Now, okay, so when you do this gauge fixing, you will find that this is all rather complicated. The Faddeev-Popov determinant has to be included here because otherwise the theory turns out you cannot satisfy unitarity. You have then to introduce ghosts, yeah, just for bookkeeping of, you know, kind of the physical degree of freedom counting. So lots of stuff. So many lectures go past. Learning all this, yeah, it's lots of fun, depending on your point of view. Now, part of the story is to learn what gravitons are. Yeah? That's essentially some essential piece that comes out of this perturbative treatment. So gravitons are the hypothetical massless spin 2 particles. So the force carriers of these linearized weak fields that appear in this perturbative construction living on Minkowski space. So again, just saying it's a graviton already means you are in the standard setting of relativistic quantum fields where you've classified particle types by the cardinal operators of the Planck array group, yeah, that gives them associated mass and spin with them. Yeah. So where does it come from, the spin 2? Well, you can trace it back to properties of the classical wave linearized wave equation that comes out of Einstein's theory. So if you make an ansatz, this ansatz G mu equal to eta mu plus H mu, then what becomes of the vacuum Einstein equations is a very simple equation if you use the right gauge, or if you use a very convenient gauge, that's the so-called harmonic gauge here. Here I've written it, so it's a first order differential equation on the H minus. Then what becomes of these very, very complicated Einstein equations, it's just the wave equation on flat space. Yeah, box H mu equal to 0. And of course, we know how to solve that. Solutions are plane waves. Now, what's special about gravity is kind of the type of wave, their polarization character. Yeah. So what is the physics of this? So first of all, you know, well, there's more gauge fixing and more subtleties, but then you end up with a very neat and simple form of this plane wave solution. Yeah, so this is kind of the 4x4 H mu seen as a 4x4 matrix, which depends only on two constants, A and B. Here you see the oscillating part. This is a wave propagating in the Z direction at the speed of light with frequency here omega. Now, so what do the A's and B's tell me? They refer to the two different polarization states of the wave. And if you hopefully recall from your GR course, the effect of a passing wave, gravitational wave, can be illustrated by putting in its way, so perpendicular to the propagation direction, to the Z direction, an array, say, of circular little test particles. And this array, you know, open your favorite textbook on GR. I don't know what that is, Carol or some other one. This gets deformed when the wave passes through. Yeah, so it gets deformed into kind of oval shaped and it kind of oscillates. And there are two linearly independent ways in which it can do it, and they're called the plus and the cross polarization. So once the circle, you know, gets kind of squished in horizontal and vertical direction, the other is kind of 45 degrees turned with respect to that. So these are the two polarization states that characterize a given wave of a given, you know, direction and a given frequency. So these are these two numbers A and B, and the polarization. I mean, we know of polarization from electromagnetic waves, but their nature is slightly different. Yeah, just because the nature of the interaction is slightly different. So they are characterized by different helicity. So the helicity here for gravitational waves is plus or minus 2. And it really refers to the behavior of these polarization states under rotation, ordinary rotation in the plane perpendicular to the direction of motion, so the XY plane. So when we come to the quantum theory, rotations, boosts, etc., of course, part again of the unitary representation of the Planck array group. And if I look at the gravitational wave, I can again understand how the one particle states, you know, of the Fock space that I'm constructing, how that behaves under rotations. Yeah, and basically in that same plane. And what is relevant there is basically just the angular momentum, kind of the J3. Yeah, and that has then eigenvalue sigma, which are plus or minus 2. Yeah, and so that characterizes then a property of this quantum state, one particle quantum state. Yeah, so that's where the spin 2 comes from. And again, it relates really to the presence of having this global symmetry around. So if I, for some reason, Minkowski space is not a good approximation. And that's a well-known phenomenon, even, studying quantum fields on non-flat spaces. You don't have a global Poincare symmetry group. You don't have a classification scheme of the irreducible representations. And you don't really know, what's a particle. At least you don't characterize it in the standard way, by mass and spin. Now, so these are gravitons, so they're elements in this box space construction. So they're perfectly well defined in the sense of kind of this mathematical sense, but you can of course ask, do they really exist? So do they really exist as single, particles? Can I detect individual gravitons, in principle and in practice? So it turns out to be a slightly gray area, but I don't think you have a good answer other than kind of heuristic arguments that have been put forward. So the typical line of argument goes, well, if I, build a detector and there should be, a decent probability that it detects these single gravitons, it will have to be very massive. And typically, very dense. So the detector I have to build to see such a graviton must have a size that is actually smaller than its Schwarzschild radius. And well, if then that is true, then you're in trouble because you yourself at your own Schwarzschild radius condensed to your Schwarzschild radius, you would of course immediately collapse into a black hole. By standard reasoning. So therefore one says, okay, perhaps this is not just impossible in practice, but it might even be impossible in principle. And therefore, and that was a line of argument that has been very much pushed by Freeman Dyson, who unfortunately is no longer with us, he would then take that as an argument to say, haha, no gravitons, no quantum gravity. But I think this is, of course, in my view, a completely wrong inference. There might very well be not a well-defined and meaningful concept of individual gravitons. It doesn't mean there is not a theory of quantum gravity. Well, it's just that it would then lie within its own event horizon, you see. So it's not really useful. I mean, not that you could build such a thing. No, not the graviton, the detector. You would have to build a detector whose specifications make it impossible even to build it, in principle. I mean, there are various, people have written papers about this. I invite you to look at them. Of course, they are all based on extrapolation of concepts you could say are, like the Schwarzschild rays are somewhat naively taken and extrapolated from classical theory. But nevertheless, it might indicate that you are in trouble and maybe the gravitons are not a very meaningful concept. Then again, if you're a string theorist, you could spend years of your life, computing scattering amplitudes of gravitons, and you think of them as very real. Yeah. Well, it exists, but only in the formal sense that, look, it's a plane wave solution, and well, we think, of wave-particle dualism, but of course, that really say for electromagnetism, that was really proven to be kind of a physical reality. It was proven that there are single photons, right? So there's something like the photon effect, where there's a bing, like for a particle. You can try and think what would be a gravito electric effect. Yeah, so an analog, yeah, you can play around with formulas, but you run typically into, needing extreme scales in your arguments, which make it, certainly impractical, but maybe even in principle impossible to make this very meaningful. Yeah, but I don't see this as a very great disadvantage. Certainly not from the point of view of a non-perturbative quantum theory. So yeah, it might be impossible to see individual gravitons, but there might very well be a quantum gravity phenomenology. Okay, I think it's a good place to stop. Okay, for a 5-minute break. See you shortly. Is everyone here? No. Okay, let us turn back to the beautiful features of perturbative quantum gravity on Minkowski space. So we've talked a little bit about gravitons, but again, this is not a comprehensive discussion. Just reminding you of things you could already know. But let me spend a little bit of time on kind of the problem, at least from a technical point of view, of why perturbative quantum gravity doesn't really work as a fundamental description of the theory. So what means this non-renormalizable? Well, one should really say more accurately, perturbatively non-renormalizable. So, and again, cutting a long story very short, right? We are, I told you, you're starting with linearized gravity. Yeah, you're setting up your Fock space quantization. Then you write the action as a quadratic piece plus perturbations, right, of higher order. Then you systematically do kind of loop expansion. So you write down the Feynman rules, say in momentum space. And then, of course, when you start computing momentum integrals, not surprisingly, you find infinities, divergences. So we're used to that from standard quantum field theory, right? And we interpret them as, well, it comes from not really having understood properly, which, let's say, which coupling constants one should have put into the theory to start with. These were just kind of formal objects in the theory I wrote down. But then in the light of kind of constructing the theory physically, these will typically have to be renormalized. And in the process, you will absorb some, if you're lucky, all of these infinities. And if you're even more lucky, well, just with a finite number of redefinitions of these coupling constants, your theory will may become finite. Now, so unfortunately, in the case of gravity, this procedure doesn't really work. And well, the simple kind of formal reason to start with, or the indication that something may not go right, comes from a dimensional argument. So the dimensional argument regards the mass dimension of the relevant coupling constant, right, that appears in the perturbation series. And that's, of course, G Newton that's relevant. And it has mass dimension -2, right, that you can, well, of course, we are working in natural units. And here, so I can write it as proportional to inverse Planck mass squared. Now, schematically, if I now, do a perturbative calculation of an amplitude of just some process where I want to understand, what are the corrections to lowest order. So, well, of course, typically I have to impose a momentum cutoff, right, just for my things to be finite. Let me call this momentum cutoff capital lambda. It should be much larger than the masses and energies of my problem. So then schematically, my amplitude will be M1 lowest order plus first order correction terms plus higher order correction terms. So in the cutoff in the momentum here, and the cutoff momentum has to appear with positive powers, because this expression clearly has to be dimensionless, like the one that's standing here. Yeah. So this being of inverse mass dimension, that leaves, this is the way it must appear schematically. What's the problem here? Well, that's a quadratic divergence, because of course I want to take away the cutoff, want to take the cutoff to infinity. this diverges. What's even worse, this gets, of course, worse at higher and higher order. So this we call kind of formally non-renormalizable, power counting, non-renormalizable, just on the basis of this dimensional argument. Now, what can happen is that you are lucky, and of course, you know, you have all these Feynman diagrams, they contribute then to whatever you know, coefficient multiplies then this contribution at a certain order, and you might be lucky and they may cancel. So coefficients might be 0. So life could be better than expected on the basis of this simple argument. And indeed, at one loop order, pure gravity is one loop finite. On shell, that means up to a term proportional to the equations of motion. That's an old result by 't Hooft and Feldman from 74. So we're talking mid-70s. However, well, so why can such cancellations occur? Typically, there will be a good reason for that. So there will be, you know, some symmetry argument for why this happens. So there are no obvious reasons for why this should happen at two-loop order. And indeed, as an explicit, the first explicit calculation was finished in '86, showed indeed there is a term, a curvature cube term that survives and that doesn't cancel against anything. And you can already see by the number of years it took to get there, that this certainly with the computational technology at the time it is a tremendous calculation. And well, I haven't written down the Feynman rules for gravity for you, but just, well, the propagator is relatively easy, say in harmonic gauge. If you look at a vertex, and there are many vertices, right? They have order 3, 4, they have like 100 terms in them. So you have a huge number of terms you need to compute. Yeah. So van der Ven verified this, had with some, was slightly more advanced computationally. But so that's the way it is. But it's a result that everyone had expected and anticipated. So, and as I said, well, once these things start being non-zero, there's absolutely no reason to believe, you know, they will then become zero, these coefficients. So one only deduces, well, there are infinitely many terms that are divergent, and each of them should, of these divergences with the standard argument, should maybe be fixed by renormalizing it, but I would have to perform an infinite number of measurements, observations to fix all those terms. When I go to the Planck scale, then all of these terms really contribute at the same order of magnitude. Yeah? And then the problem is then rephrased as saying, well, but that doesn't make sense. I have to make infinitely many measurements. Well, not that we had much quantum gravity phenomenology to speak of, but this just makes the theory lose any predictive value. Yeah? And that's when it says, okay, this cannot serve as a fundamental description of gravity, but again, in the sense of an effective theory, if I confine myself to energies that are suitably smaller, you know, compared to the Planck mass, this might be a reasonable approximation, right? So I might still get away with it for some purposes. Now the question is, right, so also when this result was known, yeah, okay, it's a technical statement, right? A certain coefficient doesn't vanish, but why? Why is the result what it is? And well, of course, then you're already on slightly speculative grounds, and you may be biased in your ideas of why this fails. But let me name a number of potential reasons that people have brought forward. So in the focus of attention is often this perturbative split, right, that you performed. You said, okay, G mu nu of x is, I just split it up into eta mu nu plus h mu nu. Well, something I can always do. So that seems innocent. I can always also do it when H becomes large, but careful. You see, it's not so good that when H becomes very large, because notice when we're looking at the space of all Lorentzian metrics, that is not a linear space, right? Because it has, the metric has a certain signature and it's not allowed to be degenerate. Yeah? So it's not true that if I add two metrics, necessarily I again get a viable Lorentzian metric. That's just not true. And if I let H mu nu become very large, of course I can easily then violate this bounds. And I would say, look, but this is a very essential thing, right? The signature of the metric. So if that signature changes, maybe when H becomes large, well, clearly you're doing something very wrong here, okay? Another potential issue is, well, presumably the theory will have some ground state quantum mechanically, but maybe it's just not Minkowski space. When Minkowski space may be much too naive. It could be something very complicated that only on sufficiently kind of large, perhaps large distance scales looks like Minkowski space, but the microstructure might be very complicated. So maybe I'm just starting from the wrong premise. So it's maybe not so much that I'm using perturbation theory, but I'm applying the perturbation theory at the wrong point, if you like. Now, yes?
What you're saying about the bounding where we try to calculate and then the applied to
No, I'm talking about, as I said in answer to the question, I'm really talking about Einstein gravity. When I say gravity, Einstein, it's Einstein gravity, not another variant. Yeah, thanks for the remark. Now, one could also argue again that it's the type of argument you're really, forcing a theory that is intrinsically geometric, talks about curved spacetime, trying to fit it into a framework, of perturbative quantum field theory, and it just doesn't fit. And that's this issue of, distinguishing a background. So here I'm distinguishing this eta mu nu background, but really, if I wanted to argue like one does classically, that seems maybe the wrong thing to do. Because what do I do classically? A priori, I don't know what a space-time is, but then I give myself, well, I look at the Einstein equation, I give myself matter content, I give myself boundary condition, I solve the theory, and I say, this is space-time. It's a solution to the equations. So by that analogy, one would say, isn't it very natural to think of quantum theory in the same way? I give you a set of quantum dynamical equations, let me call them quantum Einstein equations for better use of a word, and I then solve these, I solve the quantum theory, and what comes out is maybe something I can call a quantum space-time with some dynamics. Yeah. Well, yeah, it's an example. Yeah, this is an example of a framework exactly where you don't put in a background by hand. Yeah. So, but you have path integral versions of that where you say, well, I'm just doing I'm not putting myself. I don't only integrate over small perturbation around a given metric, which could be anything, but I allow kind of a democratic sum over all possible spacetimes, and then you have a non-perturbative path integral. So you have various ways of realizing this idea, and loop quantum gravity is also one of them in a canonical framework. Yeah. And then, of course, there's the question, since we are talking about space-time itself, Yeah, and again, as I write at the beginning of my lectures, I was invoking, microstructure of space-time, and maybe it's very quantum fluctuating, and well, how far do I, or do we expect that the framework that comes from these classical smooth metric fields remains valid, even in some effective sense? Yeah? One could be suspicious that it's maybe not sufficient if you come near the Planck scale, but it's very difficult to quantify that. Yeah? Whether you use h mu or g mu, the argument is a little bit the same. Yeah? So is it really applicable in such a regime? But then, of course, other people that bring forward other arguments that say, look, we know, okay, it looks, if I look at it in terms of metric fields g mu nu, it looks very ill-behaved, but it just means that, at sufficiently high energy, some perhaps completely different degrees of freedom will take over, and we will see that it's all a beautiful and consistent and finite theory. Yeah, so that is an example of what people usually label an ultraviolet completion of gravity. So embedding it into a larger theory, or that's how one has given meaning to that in the spirit of grand unified theories and of course of string theory. So there's a little intermezzo. So ever so often you will read maybe typically kind of a press release from some university. Their researchers have claimed that gravity doesn't need to be quantized. Okay, well, so that claims one sees regularly, and they're typically of the kind, one cannot prove that gravity has to be quantized. I find them, it makes me think a little bit of, we cannot really prove that there is climate change. So it's a little bit in that category, in the sense that it doesn't, number one, it doesn't reflect a mainstream opinion amongst people who, about high energy theorists, but it's being put forward as kind of an equivalent alternative. Well, maybe gravity is just, one shouldn't quantize it, and end of story, and we would all be so happy, right? Apart from these crazy high energy theorists, they should all be there, should become philosophers or something. So one of the more kind of serious approaches or suggestions maybe of that type is what's called semi-classical gravity. So semi-classical gravity is just left-hand side, the Einstein equations, and the right-hand side, instead of T mu nu, you work with the expectation value of T mu nu. Yeah? Then that's kind of like a classical source. And well, you can use that as an approximation, but what is sometimes claimed is, or put forward as a hypothesis, could this be, just the fundamental, the ultimate theory of gravity and space-time? So I find it very misguided. Yeah. Why? Well, really everything we have learned about nature, kind of all of 20th century physics, we've learned that, in its essence, microscopically, all interactions, all theories of matter are quantum theories, and they're described by quantum laws of motion. And as we've learned, as I emphasized at the beginning of my lecture, gravity is universal. It couples to everything. So how just immensely implausible is it that gravity just stays on the side and just stays classical? Maybe that's not, it's if that was true, so many other things were clearly misguided in how we thought about things. Maybe you have a, yes.
It is also very much because I feel that this is to really look at the physical data. No, both the general of that.
but it seems to me that it's an essentially different point. We have very good reason to understand, some of them I named, because of the weakness of gravity, of why we haven't really come to this point, and why people have, of course, thought about gravity phenomenology, as you know, why these things are not seen, our theories are too incomplete. But that's different from saying, well, sorry, I have a very realist point of view, whatever I can currently not measure probably doesn't exist. I think what I'm saying is really on the basis of how we know that physics works, and that seems to me a strong argument, right? You could, well, it's of course not a completely correct analogy, but until recently, well, we didn't have any direct evidence of gravitational waves. Let's ignore the indirect evidence we had, but then one can say, well, maybe GR is just wrong, right? But then one doesn't think about how many other things would be wrong if that was really the case, right? There are also, of course, regular claims, also typically in the press, of someone else who's shown that Einstein was probably wrong. But it's also misguided, right? Because it ignores all the stuff that weighs in favor. So I'm arguing, this is the type of argument I'm using here. So I find it's not logically impossible. I think that's also maybe the wrong way of looking at it, or at physical theory, but it seems highly implausible given everything we know. And I would say at least it would then be, I mean, people who claim that this is a plausible scenario, they should give the good reasons for why this should be so, rather than the other way around. Yeah, and if it was so, we still would need an explanation for, what happens to singularities. Can we describe the Big Bang? So what happens? That doesn't tend to be part of the argument. No, it's not. No, I agree, but I don't think it has anything to do with beauty here. It's just extrapolating. I call it extrapolating from what we know, of course, to extreme scales. And we don't know how reliable that is. Yeah, there could be totally other principles that govern physics, also at the Planck scale. And who knows? Things could become very, very deterministic, right? I mean, logically, there are many possibilities. But I'm just saying, with everything we know about physics, and I mean, really the quantum series of the other interactions. And I agree, of course, one makes extrapolations, but that's the only way we know how to argue. Yeah. Yes.
I have to finish my favor of what you say,
yes.
What you are saying.
Yes.
After all, gravity is completely different from it.
Yes.
It's a speed to field.
Yes.
And it's just the space-time. So why not? Maybe the space-time is not stable, it's not distributed. So
yeah.
That doesn't need to be quantized. I don't know whether this is a question.
Yeah.
There is no reason for this to be the same.
Yeah, but they would say, yeah, I'm perfectly happy. I think gravity, non-perturbative gravity, can be perfectly continuous. The approach I'm working with, quantum gravity, is perfectly continuous. There's no discreteness, there's no fundamental discreteness. So again, there is no contradiction there. But okay, exactly. It's not. So it was kind of an aside, slightly also to throw something mildly controversial at you. Let's go back to business. Yeah, of course. Now we are getting into deeper waters. So, isn't it so? Haven't I heard that quantum gravity must actually be part of a unified theory of all the interactions? Okay. So again, I'm probably in hot water here, contrary to what I said. So I would say, well, there is really no stringent reason for why this should be so. It's of course something that many people have thought and worked on. Yeah? So there is no reason, but again, you could say, let's extrapolate to push or to say theoretical physics necessarily will progress along the way of further and further unification. So there are two reasons, or maybe three, of why maybe this is not the case. Of course, where does it come from? It really comes from our understanding of gauge theories, right? Where we had a gradual unification. Of course, that didn't end completely happily with grand unified theories of ever bigger gauge groups, which didn't have the physical properties one was looking for. Gravity, if you want to enclose it in such a framework, there are gauge theoretic ways of writing gravity. So they do acquire also kind of a gauge in local gauge invariance. Yeah, but on top of that, you still have the diffeomorphisms that put them in a different category. So one could argue, well, maybe this type of unification, including gravity, is not the most natural thing to think about. And of course, one should also remember, with every unification, there is a price to pay, because if I postulate at some very high energies, you know that my different forces will become one. I then have to explain why at lower energies that symmetry is broken. And I would say the ugliness of some of symmetry breakings, you know, maybe compensates for the beauty of the unified aspect. So there is that. But of course, if one leaves the realm of quantum field theory, yeah, then there's of course a great, very popular dynamical unified principle, which is that of superstring theory, right? Where vibrating strings just, you know, generate all the fields we like and many more others. So in a nutshell, so one has gone down this route, but I would say the bottom line is that, of course, from the point of view of quantum gravity, where one initially hoped that string theory would be kind of reasonably unique, yeah, that was part of the beauty, that as one has learned more about string theory, it has been replaced kind of by what I call an embarrassment of riches, in the sense that you need, for consistency, to consider more and more ingredients. You need, of course, anyway, supersymmetry, you need the extra dimensions, you need many fields we've never seen, super partners, other fields, moduli fields. And string theory has lost this uniqueness, and it's also no longer seen, even by most practitioners, as kind of the theory of quantum gravity. Okay, so this, you know, kind of arguments that maybe weigh in on why the theory, the idea of grand unification is, well, again, is maybe not fruitful. Yeah. And also, I would say, of course, there are many people, you know, the word beauty was mentioned. People argue in terms of beauty. And one can argue endlessly about beauty and why, you know, the dreams of the unified theory has such an attraction, right? So I cannot help thinking of, you know, that has the flavor of this kind of, you know, monotheism to it, so that one finds it, or many people find this very appealing. But maybe the world isn't like that, or maybe it's just not a very useful way of thinking about it. Now, and not exactly the same point, but a different point is sometimes made, that, well, pure gravity, I mean, much of quantum gravity, or of non-perturbative quantum gravity, looks just at pure gravity, which means theory of empty spacetimes, yeah, where we haven't added matter to it, that in principle is just the wrong thing to do. It has a little bit the flavor of, yeah, if there's a unified principle, then of course it would be maybe a silly thing to do, but people use this argument more generally. So it has a kind of technical aspect to it. You could say, well, you know, if I add matter, then my equations will be just, or the behavior of my equations will just be changed in a way, you know, that makes all the pure gravity considerations worthless. There's also the more cosmological aspect that says, Well, if you don't have any matter, then you don't have any observers, because the observers, they have to be made from something. So there's no one to observe it, and maybe that feeds into the argument that someone just made. There is nothing to talk about. I would say, from a technical point of view, I don't think these arguments are valid, because we are very happily studying non-trivial models of pure quantum gravity, quantum geometry in lower dimensions. And many people do that. And of course, it's not physical, but these are non-trivial. They exhibit all kinds of properties that you might like from quantum theories. Obviously, I'm not saying that interaction between quantum matter and quantum gravity does not have to be understood. Obviously, and that is very, very important. Yeah, I'm just arguing against that it may not make any sense to do this without including matter. So it's of course already, classically again, Einstein gravity has non-trivial solutions. J, if we add a cosmological constant to them, so there's non-trivial stuff even classically, even in an empty space-time. Okay, now getting towards the end of the evening. Now, what do you need to construct your own theory of quantum gravity? So, is there a recipe book? Is there stuff I need as input? And what do I suggest that you use as an input, perhaps? Well, let me give you some inspiration. So the first statement is, and I think it's maybe worth emphasizing, that one has to make some choices, because otherwise one cannot even start computing. One can, of course, dream, but one cannot start computing without making explicit choices. Number one, about the microscopic degrees of freedom. Yeah, you will have some dynamics. It takes place on some kind of configuration space. So there may be kind of building blocks, fundamental fields. Yeah, so wherever the dynamics happens. And well, since we are talking about theories of space-time, maybe anything happens. So maybe we have to cast our mind a little wider of what these elementary building blocks could be. What is dynamical? Of course, the classical thing would be say, oh, just the metric or the geometry. Yeah? Well, people then argue, well, maybe it's something, with less information, maybe something that is less smooth, but maybe I have some kind of discrete or piecewise flat things where still I have notions of, say, a distance or volume, but not a smooth metric. No? Just to give an example, other structures, some discrete structure sets, causal sets, lattices of some kind. Topology. Is it meaningful to add as a dynamical local degree of freedom to the metric also topology, in the sense of, the space can hang together locally. If one talks about wormholes, interesting, that means non-trivial topology. And that, of course, is an extension. Oops, that's an extension of the standard way of thinking, but which people like to think about because wormholes have such a crowd appeal. Dimensionality. Should I fix that? Or maybe I should leave that kind of as a dynamical variable too, and somehow my system will choose its own dimensionality. Apart from, fields, there may be extended objects, apart from particles, loop strings, brane. So again, this doesn't look particularly exotic from a kind of 21st century point of view. So, but you have to fix something. No? Fundamental principles you should also fix. There are, of course, standard things that we don't question in standard quantum field theory on flat spacetime, but who knows what happens at the Planck scale. So should there still be notion of, well-defined notion of locality, causality, time? Well, without time, not much unitarity, but again, these are of course, principles that we're thinking of as very fundamental, but people like to play around, ideas, maybe at the Planck scale, these things are just not present. We have already grand unified aspect as a kind of fundamental ordering principle for the theory. So many people like to believe that the world is fundamentally discrete, or space-time is fundamentally discrete. So that might just also be put by hand into the theory. Fundamental symmetries, again, the minimal maybe standard is diffeomorphisms. Can I find ways and means to not have these diffeomorphisms? There's also an interesting question. Supersymmetry, that's of course present in string theory. Gauge symmetries, again, one can find, as I said, various gauge theoretic formulations of Einstein gravity, dualities that are present. And of course, you need a dynamical principle. So what I before called quantum Einstein equations. And here we basically have kind of two camps, the covariant R's integral and the canonical. And well, I will say more on Wednesday about specific choices. So, so choices have to be made. And one of the questions is, which things kind of have to put in by hand? Do I have a choice at all? Which could just emerge dynamically? And wouldn't it be nice, if I just start from quite random objects or very elementary objects and somehow gravity, space-time just emerge? Is that a realistic prospect? Yeah, so it raises this question. So we've talked about anyway, Planck scale is inaccessible. So this looks like a giant free lunch. You pick your favorite ingredients and oops, you have a quantum gravity theory. You make a choice from my menu. You dial a dynamical principle, and you're done. Well, very fortunately, this is not the case. So it's not an anything goes. And well, if we hadn't made progress beyond anything goes, we wouldn't really have come very far in quantum gravity. Of course, we should remember that we don't have a single kind of good candidate theory, So in that sense, maybe the world is not flooded with quantum gravity theories. And one should say, of course, there have been many attempts, but unfortunately, of course, for all of us, also practitioners, attempts are not proven to be wrong theories, but they get stuck. They get stuck because of technical and conceptual issues, and you cannot often even tell, whether what the precise reason is for why you get stuck, or is it a reason of principle? Is it a reason of just, lacking technical apparatus? But there is a strong criterion which we can use and we have used to rule out and kind of rule in certain models of quantum gravity, and which is that of the classical limit. So that's, whatever fanciful constructions you dream up at the Planck scale, you have to explain that how in a limit of large distances and low energies, you recover, important aspects of the classical gravity theory and of classical spacetime, because we know, at sufficiently low energy that this is just a very good theory of gravity. Okay. Now, unfortunately, it's not very easy when you start from some non-perturbative model to even understand what it means to take the classical limit of the structure. But with some models where you can do this, you do find that some of them give nonsense. For instance, when you have a way of computing a dimensionality and it never comes out to be anything like 4 in a large scale limit, then you tend to be in trouble. So we have criteria like this, so candidates at these ideas of how, what aspects one might be able to reproduce coming from a non-perturbative context. But yeah, so now I come to the emergence part. So in the old days, people were just talking about classical limit, right? The right classical limit. People say, okay, in loop quantum gravity, that is one example of a non-perturbative formulation. It's difficult really to understand what we mean by that. And that's a reasonably, within a quite elaborate framework, that's a reasonable way of phrasing the problem. Now, people in now invoking, quantum gravity a little bit at the level of buzzwords from all kinds of models, coming from quantum information. So you have just some, quantum bits, which are more or less structureless, and you're hoping or expressing the hope that somehow they may give rise, on large scales to things you recognize as coming from gravity or a space-time. I would say the expectations one has are very much overblown. And I'm saying this on the basis of a whole body of work that's been looked at for the last 30, 40 years, where one studies statistical models of all kinds of little building blocks with metric properties, geometric properties, and one finds that in the vast majority, these give rise to nothing you could recognize as having anything to do with space-time. And there are some very generic instabilities one runs into. And, one finds them in all places reproduced. So one has to be really careful there. One may wish, and of course we really wish for things to emerge, kind of starting from kind of unbiased, minimalistic ingredients. One could dream that somehow these ingredients with some very simple laws know that they should become gravity on large scales or resemble space-time structures. That's very difficult. It doesn't generically happen. Yeah. So what looks like Pandora's box to start with, all these choices I have at the Planck scale, turn out to be effectively much, much more constrained. I should also say, in terms of how big you make the habitat, the configuration of your quantum gravity theory, so the state space, if you like. So there is a danger if you include too many degrees of freedom, then, path integrals, that's a typical thing, but there's a complete analog if you do things canonically. They become divergent to such a degree that you cannot control it by standard renormalization. And an example of that, a very concrete example, is this idea of adding topology as a dynamical degree of freedom. So in the gravitational path integral, what is very easily done, you have, say, the sum over all spacetimes, you have e to the is. Sum over all geometries. Well, how do you include the topologies? You write another sum sign in front that says sum over all topologies. And hooray, right, you're done. The problem is, so that's an old idea, and I would say it's an appealing idea, the thing about adding the topologies, but not even in 2 dimensions has anyone been able to make sense of it. What does it mean in 2 dimensions? You have 2-dimensional space-times. Let's, for simplicity, imagine we are doing Euclidean little toy universes. Then it's a genus we are summing over, right? So the problem is the genus, if you allow space-times to have any genus, then kind of the way in which a geometry can have different topologies vastly outnumbers the way in which it can be curved in different ways. So this is just to kind of give you a flavor of what the problem is. So if you try and write down a path integral that where you allow arbitrary topologies in it, it becomes non-Borel summable. It doesn't mean we cannot invent prescriptions, you know, to make it finite, but unfortunately they tend to be not unique. And therefore, yeah, one needs a physical motivation for choosing one renormalization over another. And that's what happens in 2 dimensions. So you can imagine that in higher dimensions, this problem gets much worse. So to come back to, you know, the choice of ingredients, one may have many ideas of the beautiful things one wants to sum over, or the state space that should cover, you know, so many eventualities. If it's very big, typically you can't do anything with it. You know, it's just too, you cannot handle it. If it's too small, maybe if your model is too simple, then you run the danger of not recovering the local degrees of freedom of this complicated classical theory. So in reality, you know, yeah, you're actually tied down, although it's sometimes not immediate to see that your theory has problems in one way or other. Okay, that's the last. Very good. The last question of the day. So how has quantum gravity developed historically? So I already mentioned to you that really the first papers, right, were written by Bornstein and Rosenfeld, 1930s, 1936, Matvei Bornstein's thesis, basically kind of writing down perturbative quantum gravity, but of course, without knowledge we have today, right, especially about the infinities and how to interpret those. What happened between the 1930s and until, you know, the late 1970s, no one was very much interested in quantum gravity. I mean, there was, of course, QED was the big game in town, right? And Feynman made some very disrespectful remarks about people who are interested in gravity. I think that was like the 60s. One just didn't, that was not considered an interesting thing to do. I mean, neither classical nor quantum. So then, of course, there was a whole boom of understanding non-abelian gauge series, the 70s, 80s, also the triumph of the gauge principle. And there, well, there is a kind of, there stuff starts happening in quantum gravity too. So I mentioned, you know, 70s, by the late 70s, people understood that perturbative quantum gravity is not the fundamental theory, as I explained to you before, mentioned to you before. So there things branch off into kind of non-perturbative covariant approaches based on G mu nu, basically path integral, and canonical approaches, where one should also say particle physicists were going down this way, and this is much based coming also from the classical VR community. Yeah, people familiar with even what it means to canonically formulate classical gravity. Okay, so now, so what is here? So lattice approaches, the huge success of, say, lattice quantum field theory, lattice QCD, one tried to emulate for gravity. Euclidean quantum gravity, you know, that is Hawking et al. Cambridge, big boom, 70s, early 80s. Later, of course, superstrings as a natural development, really also within, you know, particle physics, that part of the community. In parallel, well, canonical quantum gravity, that from the 80s onwards, roughly at the same time as superstring theory here on that left-hand side, became kind of the canonical way of doing quantum gravity. So one started canonical gravity, but just by, you know, GIJ hats and pi ij hats. So these are the spatial metric and momenta after space-time decomposition, ADM decomposition. So what one tries to make sense of here in these covariant things, roughly speaking, are path integrals, yeah, sum over all configurations e to the is, in some way, what one tries to do here is solve the Beer-DeWitt equation. So that's kind of the two different dynamical principles that take very different forms, but I'll explain some of that on Wednesday. There are definite common issues and problems, and the key ones are, well, how, if one really wants to go beyond perturbations, what are the correct tools? What does one need? What is realistic? How can we understand the theories? And then a theme I'll come back to is that of diffeomorphism invariance. Namely, how do I implement diffeomorphism invariance in a way that's compatible with how I regularize and renormalize the theory? And this is an essential difficulty. And we'll get back to the whole beautiful story on Wednesday. So thank you very much.
Very nice introduction to the discussion and look at. Probably the case would be that when we think about quantum work, classical theory, high-dimensional, I mean, all this idea about anything here, but then probably open the field to that direction. At the end of the day, it doesn't work because the extra dimensional gravity still needs to be divided by so still needs to be quantum. But just very itself, perhaps, it's another completely different way of thinking. But we think it's quantum and affects theory on four-dimensional.
I mean, there are many viable ways, yeah, but also I would say, and I don't value things on an absolute scale, but of course, we have seen, parts of the community going in one way, getting somewhat dispersed. So there may, I would say, as I said right at the beginning, it's as long as I've been practicing gravity, I've heard these arguments that people shoot each other down because it's clear this model cannot be right, and then comes some criticism on the ingredients and the setup. Yeah, I would say, well, and it hasn't been very helpful. But in absence of anything else, that was all that people get agitated about all the time. So if we manage, as a collective group, to move the direction more into what, hey, can we identify things we can compute? Yeah. And in this framework and that framework, and we can compare some numbers. That would make that discussion much healthier. Yeah. So yeah, I have high hopes that we're moving in that direction, but yeah, but also the general development, right? That although it's maybe over-optimistic and far-fetched, but trying to think about, can we use gravitational waves? Can we think about, what happens in these strong gravity processes? Anything that could have an influence of quantum effects. Yeah, wouldn't that be nice? And you see people are gravitating towards these topics, coming from quite different corners, just suddenly thinking, okay, maybe it's about physics after all, quantum gravity, and maybe, we can make a connection. Yeah. Yes. I didn't understand the question. I heard just wave something. You said something about waveforms. Well, we wish we knew, but yeah, of course. But of course, the problem being there that as things currently stand, it will be very difficult to distinguish. The waveform is the waveform. It has some information. Signals can have many explanations. Also, of course, people think about modified. That goes back to the modified gravities. Yeah, and but there are, again, at this stage, I would say, I've seen some of these papers, so heuristics, but I find it very appealing because I'm working on quantum gravity. I'm working on, non-trivial dimensions, computed with space-time, to ask oneself, well, could this leave an imprint on, say, gravitational waves that reach me from very far away? I mean, the problem always being that there are other competing explanations which may have absolutely nothing to do with quantum gravity. Could be astrophysical. So there are pitfalls, but yeah, I think we should be more hopeful than we've been for a long time. I know. I looked. Yeah. Yeah. But there, I've looked at some of the papers, also some of the papers you've been involved in. I mean, of course, we have to be honest also to say that we have still a problem on the theory side, that our theories are too incomplete, and we have to, use some ad hoc assumptions.
Of course, the better you get the generality, the worse
Yeah.
the worse the method on the theoretical side.
Yeah, but really also stuff has to happen on the theory side, that we are can be more certain, really pinned down without ad hoc assumptions what we are predicting. Yeah, but I think it's very interesting ideas. Oh yeah, okay.
What's your opinion about the evidence in quantum gravity?
The what?
The evidence.
Yes.
The interpretation of quantum mechanics.
Yeah.
So we assume that we are the quantum mechanics group also. So it's combined.
Yeah. Yeah.
Now, you said your opinion about the alternative QGR. But I didn't hear something about the quantum mechanics side.
Yes.
What is it?
Yeah. Yeah. I don't see any, it comes a little bit back to the question about are the principles of quantum theory incompatible with the fundamental theories underlying GR? Is that the correct way of interpreting it? Or that could also include, what's the status of the measurement problem, things like this? Yeah, I see, really from kind of a quantum field theoretic point of view, where I don't necessarily describe the full universe, at any given time all the time, but I'm just interested in local quantum gravitational dynamics. I don't see any fundamental reason why not, fairly standard quantum theory wouldn't be applicable. In the sense, obviously, that we have to understand how to treat dynamical geometry. But the fact that, we're still, when at the end of the day, we're still talking about Hilbert spaces and, describing spectra of self-adjoint observables in a quantum field theoretic interpretation, and some kind of maybe quite non-trivial vacuum. I don't see why this shouldn't work. All right, no raised hands. Thanks for the good questions. See you later.